I'm going to help you on homework 0. This problem that I'm going to start with, the technique is very similar to number 1, the same thing that you should do in that problem. It kind of looks a little different, but it ends up being a very similar problem. So taking a look at this problem, we have the integral from 0 to 1 of x over the quantity x squared minus 4. So what you should always look to do first is see, is the inside function here something that I know the integral of immediately, or in other words, what is the antiderivative of what's circled there? Well, this is kind of complicated, it's not obvious, so that doesn't work. Then you ask yourself, can I simplify that so that I have pieces separated by adding and subtracting, that then I can evaluate the integral of each of those and it's easy? Answer to that is no for this one. So after we've explored those things, the next thing you should look at is substitution, which is section 5.5. Another option is 7.1 by parts, but usually it's a good idea to look at substitution first. It's not obvious that substitution would be used on here. Usually substitution, just to speak to that a little bit, if you know what substitution is, you can kind of ignore this for a second, but in general what the substitution technique is when you have an integral of a composite function, which is f of g of x, times the derivative of the inner function. If that's the form of your integral, then you can use substitution of a variable, u, for g of x, and then what you end up having is a function f of u du, which hopefully you know little f of u's antiderivative or integral because it's simpler, and then this g prime of x thing is not there anymore because it's contained in the du, and then so this big F is the antiderivative or slash integral. I'll just put my plus c there, and then you can do that. That is the basic substitution technique. That formula isn't given so much in Calc 2 because it actually can be more complicated than that. And we'll go into that in class a little bit with an example, but for now let's just kind of try to see if we can deal with this with the basics. So anyway, going back to this example, it's not obvious that there is a composite function here. It doesn't mean that substitution can't be used. Another thing to look for is, do I have some function in terms of x that I can identify with u such that the derivative of that function is there times that f of u function. So if you look at that, notice that in the denominator you've got x squared minus 4, and if you take the derivative of that you get 2x. So 2x is not quite x, and it turns out if it's just a multiple of 2 there, a factor of 2, not multiple, 2, factor 2, then you can fix that. So the variable part of that, if that's there, substitution's going to work, usually. So right there we determine, like, hey, substitution's probably going to be a good thing. Another thing you can do is actually write this as a composite function. This is equivalent to x times x squared minus 4 to the negative 1. So you don't necessarily have to do that initially, but the u is usually the inside of the composite function, which now it actually is written that way. So that was sort of what I was thinking about anyway when I was trying to identify the u, and the derivative kind of is present. 2x, without the 2 it's x. This is going to work, probably. Alright, so anyway, my u, x squared minus 4, so kind of the things I was saying, we're going to actually pursue this now because it seems like it's good thing. So the way that you find the du is you take the derivative of u, and I'm using Leibniz notation here. So the d over dx is saying I'm taking the derivative of u. So altogether is du over dx. And then take the derivative, you get 2x. And then to rewrite it as a differential, you just multiply both sides by dx. So you have du is equal to 2x dx. And now I go back to my integral and I start trying to write this in terms of u. So the goal of substitution technique is to do a change of variables, and the variable name we use is u, so that you have an integral that is easy to evaluate in terms of u. So far with our choice of u, we have u to the negative 1 here, and then now what we need to do is you have to do a legit substitution for the du. It's not always just dx. So if you look at what we have here, this is what we were working on here, is we want to make the substitution for dx. That's going to be part of the du. So notice it's right here. So it's there. And then we have to have the variable part here, x, present as well. So times that x is there. But there's no 2. And that's okay. Turns out we can just do some algebra here. It's one way to take care of this, and divide by 2. And then your little formula here is that to write this integral in terms of u, that you're going to use du over 2 substituted in for x dx. So what we just figured out is how to write this integral in terms of u. Oops. Meant to write du over 2. So u to the negative 1 times du over 2. So we did that in a legit way with a change of variables to write this integral in terms of u. Now if we know that integral, we can do it in terms of u. And it turns out we do know that integral. So this is a really good approach, and we're going to be able to finish this. Now with that being said, we do have these little numbers here which are called the limits of integration. And I'm going to be legit here. Those are in terms of x. So if I'm writing my integral in terms of u, those are no longer the values that go in there because they're x values. I need u values because my integral needs to be entirely in terms of u. So for now it's kind of a notation thing. I'm going to show you how to do this 2 ways. But to be legit, I'm going to write that in. Remember that u is equal to g of x, so this is just a way to say, like, hey, it's not 0 and 1 anymore because those are x values, but I could convert them to u's and have this whole integral in terms of u. If I let u equal g of x, then that would be g of 0 and g of 1 to get in terms of u. Alright, so I don't want to lose sight of the important things here. I'm just going to keep going with this technique, and then I'll backtrack on how you can do this a different way with the g of 0 and g of 1 thing. So for now, note that you can pull out a 1/2, and hopefully you know the integral of u to the negative 1. And so you should. It's maybe a little bit in disguise. Sometimes people write it as 1 over u. If you still don't recognize it, this is one of the integrals that you should know. This integral is ln of the absolute value of u. So memorize that the integral of 1 over u, or the integral of u to the negative 1, or normally an x, integral of x to the negative 1, is ln absolute value of x, or in this case, absolute value of u. So we are almost there. Now what we need to do is remember that, oh yeah, I had these little numbers in here. Just carrying along my g of 0, my g of 1. And then the notation here, or one notation is, I need to plug these numbers in. Still, use the fundamental theorem of calculus part 2. Now after you do the integral, you can go back in terms of x. So your u is equal to x squared minus 4 and you can go ahead and plug back in terms of x, and then guess what? Your limits of integration go back to x's. So this is one way to handle this substitution, with the limits of integration in their little numbers. Okay, so I'm going to leave the 1/2 out, and then I have ln of the absolute value of 1 squared minus 4 minus ln absolute value of 0 squared minus 4. This is Fundamental Theorem of Calculus Part 2. Tells me to do that. Then I have 1/2 ln of 3 minus ln of 4. And because we like to write exact answers, that's actually good enough. Technically you can simplify this, which I'm not going to expect that you do this, but if you want to be real fancy, you could do a little log algebra and write it like this. So that's it for this example, but I do want to backtrack to an alternative method with plugging in the numbers at the end. And it's good for you to know both ways. Get comfortable. Let's see here. Going back here. So going back to this step, you do it the same way. But then you do a little side work here and say, what is g of 0 and what is g of 1? So you use the g of x again, just to be clear that your g of x, or your u, is x squared minus 4 from the beginning. So that's what you're using there. So your g of 0 would be 0 squared minus 4, which is negative 4. And your g of 1 would be 1 squared minus 4, which is negative 3. So then what you would do at this stage is actually find those numbers in terms of u. Make sure you put them in the right place, because sometimes they can change order on least to greatest. So the g of 0 is what went down low, and the g of 1 was negative 3. So just put them, this was g of 0 down low, that's what goes down low. G of 1 goes on top. Always. So now looking at this, everything is in terms of u. And so you do not want to go back to x. And you're just going to plug in your u values and call it a day. So you have ln absolute value of 3 minus ln absolute value of 4. So we have 1/2 ln 3 minus ln 4. So same thing as before, as it should be. And you can see it's pretty much just this step right here rolled up here instead of doing the side work. So it's just a different way of doing it, but it's nice to have competency in both ways. Sometimes one way is shorter than the other, and we're going to be using what's called inverse substitution in 7.3 already, and so just kind of really having some know-withal with all the limits of integration stuff is kind of a good exercise. So that's it for that example.